Close your eyes for one moment and imagine this. You are floating in the infinite void of space, surrounded by the absolute silence of the cosmos. In front of you, billions of stars flicker like diamonds scattered on black velvet. And then something extraordinary happens. You begin to accelerate faster than any rocket, faster than any comet, faster than anything humanity has ever created. The stars start to stretch out, transforming into lines of pure light. The entire universe is transformed before your eyes, because you are about to achieve the impossible, traveling at the speed of light. This fantasy has captivated humanity ever since we understood that light has a velocity, 300,000 kilometers per second, a monumental figure that our minds can barely comprehend. It is fast enough to circle the Earth more than 7 times in a single second, fast enough to travel from here to the Moon in just over 1 second, fast enough to reach the Sun in barely 8 minutes. And yet, on the scale of the universe, even this dizzying velocity is terribly slow. The light from the nearest star takes more than 4 years to reach us. That from distant galaxies, billions of years. But what would actually happen if you could travel at that velocity? Not in the technical or engineering sense, but in the deepest and most fundamental sense. What would happen to time? What would you see? How would your own existence change? The answers to these questions lead us to one of the most revolutionary and beautiful discoveries of science, Einstein's special relativity, a theory that revealed that space and time are not what they seem, but something much stranger and more marvelous. Today, we will embark on a contemplative journey through these ideas, not with intimidating equations or technical jargon, but with the tranquility of someone observing the stars on a serene night. We will explore together what physics reveals about the deepest nature of reality, and why this cosmic speed limit is not a prison, but perhaps the most extraordinary gift the universe could offer us. Welcome to this space for nightly reflection, where science meets contemplation. If you enjoy exploring these mysteries of the cosmos with a voice that accompanies you in the stillness of the night, consider joining our community at Ciencia Nocturna. Here, every night, we decipher together the most fascinating enigmas of the universe, one at a time, with the unhurried pace that true understanding deserves. Now, breathe deeply, let your mind expand toward the infinite, and let us begin our impossible journey toward the speed of light. Before Albert Einstein changed everything in 1905, the world seemed a much simpler place. Time flowed the same for everyone everywhere. Space was a fixed and immutable stage where the events of the universe occurred. And velocity was just a matter of adding and subtracting. If you were running at 10 kilometers per hour on a train traveling at 100 kilometers per hour, your velocity relative to the ground was simply 110 kilometers per hour. Logical, intuitive, obvious. But there was a problem so fundamental that it threatened to destroy all of physics as it was then known. And it all began with light. During the 19th century, physicists had discovered something extraordinary about light. It traveled as a wave through space. Waves in the water need water to propagate. Sound waves need air. Therefore, scientists reasoned, light must need some invisible medium that filled all of space. They called it the luminiferous ether, a mysterious and omnipresent substance through which light propagated like waves in an invisible ocean. If the ether existed, then it should be possible to measure how we move through it. Imagine you are swimming in a river. If you swim downstream, you move faster than if you swim upstream. Similarly, they thought, if the Earth moves through the ether, the velocity of light should be different, depending on whether we measure it in the direction of the Earth's motion or perpendicular to it. In 1887, two American scientists, Albert Michelson and Edward Morley, designed a brilliant experiment to detect this effect. They built an instrument so sensitive that it could detect minuscule differences in the speed of light. They calibrated it meticulously. They took measurements over and over at different times of the year when the Earth was moving in different directions around the Sun. The result was bewildering. They found nothing, absolutely nothing. The velocity of light was exactly the same in all directions, regardless of how the Earth was moving. It was as if you were swimming in a river and discovered that your velocity is exactly the same whether swimming upstream or downstream. It made no sense. For nearly 2 decades, the world's brightest physicists attempted to explain this puzzling result. Some proposed that the Earth dragged the ether with it, like a ship drags water. Others suggested that objects physically contracted in the direction of their movement through the ether, exactly compensating for any difference in the velocity of light. These were ingenious explanations, but they seemed forced, artificial. And then came Einstein, a young patent office clerk in Switzerland, 26 years old, without access to sophisticated laboratories or prestigious academic positions. But he had something more valuable, a mind willing to question the most fundamental assumptions about reality. Einstein proposed something radical. What if the ether simply doesn't exist? What if the velocity of light does not depend on the motion of the source or the observer, but is a fundamental constant of the universe? What if 300,000 kilometers per second is not just the speed of light, but the maximum speed limit for anything in the cosmos? This simple idea had astonishing consequences. If the velocity of light is constant for all observers, no matter how they move, then something else has to change, and that something turns out to be space and time themselves. Think of it this way. Imagine you are standing at a train station, and a train passes in front of you at high speed. Inside the train, someone shines a flashlight pointing forward. According to classical physics, the light from that flashlight should travel at the speed of light, plus the speed of the train. But according to Einstein, no matter how fast the train moves, the light still travels at exactly 300,000 kilometers per second. No faster, no slower. How is this possible? The only way is for time itself to flow differently for you, standing at the station, and for the person on the train. Time inside the moving train must pass more slowly from your perspective, exactly enough, so that light always travels at the same speed, regardless of the observer's motion. This is the essence of special relativity. Space and time are not absolute, but relative. They stretch and compress, depending on how you move. And the faster you move, the more dramatic these effects become. At everyday speeds, these differences are imperceptibly small, but as you approach the speed of light, the effects become increasingly extreme, until finally, at the impossible limit of the speed of light itself, time stops completely and space contracts infinitely. But there is something more, something even more fundamental. Einstein discovered that energy and mass are different manifestations of the same thing, related by his most famous equation, $E equals mc circumflex $2. The speed of light appears here too, squared, connecting mass with energy, and this equation reveals why nothing with mass can reach the speed of light. As you accelerate, your kinetic energy increases, but due to relativity, part of that energy is converted into additional mass. The faster you go, the more massive you become, and the more massive you are, the more energy you need to keep accelerating. It is a vicious circle that intensifies exponentially as you approach the speed of light. To reach exactly the speed of light, you would need infinite energy, not just a lot of energy, or more energy than humanity can generate, but literally infinite, more energy than is contained in all the stars of all the galaxies in the observable universe. It is an absolute mathematical impossibility. The speed of light is not just fast, it is a fundamental barrier woven into the very fabric of space-time. It is the speed limit of the universe, not because no one has figured out how to go faster, but because faster literally has no meaning. It's like asking, what is north of the North Pole? The question itself is meaningless, and yet, light itself travels at this velocity. Photons, massless particles of pure light, cross the cosmos at 300,000 kilometers per second, not because they are especially fast, but because it is the only velocity at which they can exist. For anything without mass, the speed of light is not a limit. It is the only option. This realization fundamentally changed our understanding of the universe. Space and time are not the stage where events occur, but active participants in the cosmic dance. The speed of light is the thread that binds them, the limit that defines the possible from the impossible, the real from the imaginary. And now that we understand why this limit exists, we can begin to explore what it would mean to attempt to reach it. What would happen to your body, to your perception, to time itself? Prepare yourself, because the journey we're about to undertake will challenge every intuition you have about reality. Imagine for a moment that you have access to all the energy of our sun, not just the light that reaches us every day, but all the energy contained within its burning core, all the nuclear fusion that has sustained life on Earth for billions of years. It is an almost inconceivable amount of energy. Every second, the sun converts 4 million tons of matter into pure energy. 4 million tons every second. Now imagine that you can harness all that energy and use it to accelerate a spaceship, a small ship, say, the size of a car, with a mass of approximately 1,000 kilograms. How close to the speed of light could you get? The answer is surprising and devastating. Not even close. To understand why, we need to delve into one of the strangest and most beautiful consequences of Einstein's relativity: relativistic mass. In our everyday experience, the mass of an object is constant. 1 kilogram of apples weighs the same, whether it is stationary in your kitchen or if you carry it in a car at 100 kilometers per hour. But this is only because we move so slowly in comparison with the speed of light that relativistic effects are imperceptible. As an object accelerates and approaches the speed of light, something extraordinary begins to happen. Its effective mass increases, not because you are adding matter, but because the energy of the motion itself is manifesting as additional mass. Remember Einstein's equation, $E equals mc circumflex, $2. Energy and mass are two sides of the same coin. When you add kinetic energy to an object, you are also adding mass. At low velocities, this effect is insignificant. At 100 kilometers per hour, your car gains approximately 1 part in 1 billion of its original mass. It is so small that no instrument could detect it. But as you approach the speed of light, the effect skyrockets dramatically. When you reach 90% of the speed of light, your mass has more than doubled. At 99%, your mass is 7 times greater than when you were at rest. At 99.9%, 22 times greater. And as you get closer and closer to that final barrier of 300,000 kilometers per second, your mass grows without limit, approaching infinity. This creates a fundamental physical problem. To accelerate something, you need to apply force, and the amount of force required depends on the mass of the object. But if the mass of the object increases as you accelerate, you need more and more force to achieve each small additional increment of velocity. It is like trying to climb a mountain that gets steeper with every step. At first, the path is relatively easy, but soon each step requires twice the effort of the previous one, and then 4 times more, and then 8. And the slope becomes increasingly vertical, approaching an infinite wall that you can never climb, no matter how much energy you have. Let's do some contemplative calculations. Suppose we want to accelerate our 1,000 kilogram ship to 90% of the speed of light. Using the equations of special relativity, we can calculate how much energy would be required. Approximately 10 to the power of 20 joules. That is 100,000 million billion joules. To put it in perspective, it is roughly equivalent to the energy that all of humanity consumes in several months. That is only to reach 90%. What about 99%? The required energy shoots up to approximately 3 times 10 to the power of 20 joules, nearly triple the energy to gain only an additional 9% of velocity. At 99.9%, you need approximately 10 to the power of 21 joules, 10 times more energy, to gain only an additional 0.9%. Do you see the pattern? Each additional decimal of proximity to the speed of light requires exponentially more energy. It is a curve that shoots up towards infinity, asymptotically approaching but never reaching that final limit. To reach exactly 100% of the speed of light, you would need literally infinite energy. Not a lot of energy, not more energy than exists in the universe. Infinite, an absolute mathematical and physical impossibility. But even if we could somehow bypass this limitation, there is another, equally fundamental problem. Where would all that energy come from? Let us consider the most powerful energy sources we know. Nuclear fusion, the process that powers the sun and all stars, is the most efficient energy source that occurs naturally in the universe. It converts approximately 0.7% of mass into energy. It is incredibly efficient compared to chemical combustion, which converts only 1 part in 1 billion of mass into energy. But it is still not enough. Even if you built a perfect fusion engine and used all the fuel as propellant, you would reach perhaps 10 or 20% of the speed of light before running out of fuel. To go faster, you would need something even more efficient. Antimatter offers the theoretical limit of energy efficiency, 100% conversion of mass to energy. When matter meets antimatter, both are completely annihilated, transforming into pure energy. According to $E equals mc circumflex, $2, it is the most powerful energy source permitted by the laws of physics. But even with antimatter, the numbers are daunting. To accelerate our 1,000 kilogram ship to 99% of the speed of light, using a perfect antimatter engine, you would need approximately 1,500 kilograms of fuel, 750 kilograms of matter, and 750 of antimatter. That means your ship now weighs 2,500 kilograms in total, which means you actually need even more fuel. It is another vicious circle. When you do the complete calculations, considering that you have to carry the fuel with you, the total mass of your ship at the start of the journey would be astronomical. To reach 99.9% of the speed of light, you would need your initial ship to weigh hundreds of thousands of tons, almost all antimatter fuel, just to move a 1,000 kilogram capsule. And here is the additional problem. Antimatter does not exist naturally in significant quantities in the universe. We have to create it artificially, in particle accelerators, and the process is extremely inefficient. It requires 1 billion times more energy to create antimatter than you get when you annihilate it. Currently, humanity has produced only a few nanograms of antimatter in all its history. We would need thousands of tons. Even if we solved all these technical problems, we would still face the fundamental barrier. As you approach the speed of light, each additional fraction of a percent requires exponentially more energy. You could use all the energy of all the stars in the Milky Way, and it still would not be enough to accelerate even a single atom exactly to the speed of light. This is not a technological limitation that we might one day overcome with better engineering. It is a fundamental limitation of the universe itself. The infinite energy barrier is as real and insurmountable as any law of nature. But there is something deeply beautiful in this limitation. The universe is not arbitrary. It does not allow some things to happen and forbid others on a whim. Instead, everything flows from elegant and consistent mathematical principles. The speed of light is special because it connects space with time, energy with mass, cause with effect. It is the thread that holds together the fabric of reality. And although we may never reach it, the simple fact that this absolute limit exists tells us something profound about the nature of the cosmos. It tells us that the universe has a structure, rules, symmetries. It tells us that there is order in the apparent chaos, patterns in the complexity. Photons of light can travel at this velocity, not because they are especially powerful, but because they are massless. For them, 300,000 kilometers per second is not an impossible goal. It is the only form of existence they know. They are born traveling at this velocity and die traveling at this velocity. They never know stillness. They never know slow motion. For them, the entire universe is a timeless instant. But for us, beings of mass and matter, anchored in the flow of time, the speed of light remains eternally out of reach. No matter how much energy we have, no matter how advanced our technology becomes, it is a horizon that recedes as we approach, always the same distance away, always unattainable. And yet, we can get closer. We can build particle accelerators that propel protons to 99.99% of the speed of light. We can observe cosmic rays that travel even closer to this limit. We can study these phenomena and learn about the extreme physics near the cosmic barrier. And in our imagination, we can go even further. We can explore what would happen if we could somehow travel at these extreme velocities. What would you see? What would you feel? How would your experience of time and space change? That is the journey we will continue now, knowing that although the final destination is impossible, the path to it reveals extraordinary truths about our universe. There is a famous paradox in physics that perfectly illustrates how strange time becomes when you approach the speed of light. It is called the twin paradox, and although it is called a paradox, it is not contradictory at all. It is simply so counterintuitive that it challenges everything our everyday experience tells us about how time works. Imagine two identical twins. Let's call them Anna and Beatrice. Anna decides to stay on Earth, live a quiet life, raise a family, age under the same sky she has known all her life. Beatrice, on the other hand, is adventurous. She boards a spaceship capable of traveling at 99.9% of the speed of light and undertakes a journey to a distant star. From Beatrice's perspective inside the ship, the journey lasts, say, 2 years. 2 years of her personal life, measured by her clock, by her heartbeat, by the number of times she sleeps and wakes up. 2 years, according to any subjective measure of time she can experience. But when she returns to Earth and reunites with her sister, she discovers something astonishing and terrible. Anna has not aged 2 years. She has aged 45 years. Anna is now a middle-aged or even elderly woman, while Beatrice is still young, barely 2 years older than when she departed. How is this possible? How can two clocks, both functioning perfectly, both measuring the same physical phenomenon called time, arrive at such dramatically different answers? The answer is at the heart of special relativity. Time is not absolute. It does not flow at the same speed for everyone, everywhere. Instead, Time is relative, dependent on how fast you move through space. And the faster you move, the slower your time flows in comparison with someone moving more slowly. This phenomenon is called time dilation, and it is not an illusion or a measurement trick. It is as real as gravity or electromagnetism. Time literally elapses more slowly for moving objects. At everyday speeds, the effect is infinitesimally small. If you fly on a plane around the world, your clock will lag by approximately a few nanoseconds compared to a clock on the ground, but the effect is real and measurable with sufficiently precise atomic clocks. As you approach the speed of light, however, the effect becomes dramatic. There is an equation that describes exactly how much time slows down, and it is called the Lorentz factor. Without going into the mathematical details, what you need to know is this. At low velocities, the factor is approximately 1, which means time flows normally. But as you approach the speed of light, the factor grows without limit. At 50% of the speed of light, time flows at approximately 87% of its normal speed. 1 hour for you is approximately 1 hour and 9 minutes for someone at rest. Interesting, but not dramatic. At 90% of the speed of light, 1 hour for you is 2 hours and 18 minutes for someone at rest. Now it is becoming significant. At 99%, 1 hour for you is 7 hours and 5 minutes for the outside world. A full day of your life is equivalent to a week for everyone else. At 99.9%, 1 hour for you is 22 hours and 24 minutes for the rest of the universe. 1 day of yours is almost a month for Earth. And as you get closer and closer to that final speed barrier, the effect intensifies exponentially. At 99.99%, 1 year of yours is equivalent to 70 Earth years. At 99.999%, 1 year of yours is 224 years for Earth. At the impossible limit of the exact speed of light, time stops completely from the perspective of the rest of the universe. A journey that lasts an instant for you spans the entire age of the cosmos for everyone else. It is an infinite discontinuity, another indication of why nothing with mass can cross this barrier. But why does this happen? What does movement through space have to do with the flow of time? The key is to understand that space and time are not separate entities, but aspects of a single, unified entity called space-time. We all move through space-time at a constant velocity, the speed of light, always, without exception. This sounds strange, so let me explain. When you are sitting still, you are not moving through space, but you are moving through time at your maximum velocity, 1 second per second. All your motion through space-time is dedicated to moving forward in time. But when you start to move through space, some of that motion has to be redirected from time towards space. It is as if you have a fixed budget of velocity through space-time, and you have to decide how to divide it between spatial motion and temporal motion. The faster you move through space, the less velocity you have left to move through time. Your clock slows down because you are literally using your temporal motion for spatial motion. It is a fundamental trade-off: space for time, time for space. At the extreme limit, if you could move all your velocity from time to space, you would be traveling at the speed of light through space and at zero velocity through time. Time would stop completely, but only something without mass can do this: a photon, a particle of pure light. This exchange between space and time also explains why the speed of light is the same for all observers. No matter how fast you move, you are always traveling through space-time at the same total velocity, the speed of light. Only how that velocity is divided between the spatial dimensions and the temporal dimension changes. The practical consequences of this are astonishing and a little melancholic. Imagine you are an astronaut on a mission to a nearby star, say Proxima Centauri, 4.2 light-years away. You travel in a ship that can accelerate continuously at 1 g, the same acceleration you experience on Earth due to gravity. From your perspective inside the ship, the journey takes approximately 3.5 years. Not bad. You leave Earth as a 30-year-old person and arrive as a 33-year-old person. You explore the star system for a year, then return. Another 3.5 years of travel. Total, 8 years of your life. But when you arrive home, you discover that 12 years have passed on Earth. Your friends and family are noticeably older. The children you left behind have become teenagers or young adults. The world has changed in ways you cannot imagine. You have traveled not only through space, but also into the future. And this is with a relatively short journey. Imagine a mission to a more distant star, say 500 light-years away. If you travel sufficiently fast, you could make the round trip in, say, 20 years of ship time. But when you return to Earth, more than 1,000 years will have passed. The entire civilization you knew will have disappeared. You would be more isolated from the world you left than any historical explorer. This is the price of interstellar travel at relativistic velocities. You not only cross space, but also time. You become a temporal traveler, pushed inexorably into the future with no possibility of return. There is something deeply poetic and tragic in this. The universe allows you to explore the stars, but only if you are willing to abandon your own time, your own era. You can see the future, but at the cost of losing your present. It is as if the cosmos were telling us, you can have space, or you can have time, but you cannot have both completely. And yet, from a certain perspective, this is also beautiful. It means that the future is real and accessible. Time is not just an illusion or a human construct. It is a physical dimension of the universe, as real as the spatial dimensions. And we can navigate through it, at least in one direction, by varying our velocity through space. For the photons of light that travel always at the maximum velocity, time does not exist at all. A photon emitted in the Big Bang and traveling for 13.8 billion years until it reaches your eye experiences no time whatsoever from its own perspective. For the photon, its creation and its absorption are the same event, separated by zero time. It exists in an eternal present, oblivious to the passage of eons. We, trapped in our mostly temporal motion through space-time, experience the flow of time as something inexorable. Second after second, minute after minute, we always move forward. But near the speed of light, this flow becomes a drip, and at the impossible limit of the speed of light itself, the river of time stops completely, frozen in an eternal instant. It is a limit that we can never reach, but one that we can approximate. And by doing so, we become time travelers, navigating the currents of space-time towards distant futures, leaving behind everything we knew. Close your eyes and imagine you are looking out the window of your spaceship. In front of you, the cosmos stretches out, an infinite tapestry of stars scattered across the black void. Some shine brightly, others barely flicker. You recognize familiar constellations, patterns that humanity has observed for millennia. The universe seems quiet, eternal, immutable. Now, imagine you start to accelerate. Slowly at first, then faster and faster. 10% of the speed of light, 20%, 50%. And, as your velocity increases, something extraordinary begins to happen. The universe itself starts to transform before your eyes. It is not just that the stars pass faster, it is something much stranger and more fundamental. The very geometry of space around you begins to distort in ways that defy all intuition. The cosmos you knew becomes something completely alien, a landscape of extreme physics that no human eye has ever witnessed. The first change you would notice is aberration of light. It is an effect related to how velocities combine in special relativity. When you move very fast, light coming from different directions appears to change its angle. The stars that are in front of you, in your direction of travel, seem to move even more forward, concentrating increasingly toward the exact point you are heading for. At the same time, the stars behind you seem to move even further back, moving away from the center of your field of view towards the edges. It is as if the entire universe were being sucked into a focal point in front of you, while it expands and stretches behind you. At moderately relativistic velocities, say 50% of the speed of light, this effect is noticeable but not dramatic. The constellations look distorted, stretched in the direction of your travel, but you can still recognize patterns. You can still orient yourself, but as you accelerate more, 70, 80, 90% of the speed of light, the effect intensifies dramatically. The stars in front of you begin to cluster in an increasingly small circle directly in front of you. Stars that were originally 90 degrees from your direction of travel, that is, directly to your side, now appeared to be 45 degrees ahead. The entire night sky is compressing forward. At 99% of the speed of light, almost all the stars in the visible universe are compressed into a small circle, approximately 30 degrees wide, directly in front of you. It is as if you were looking through a tunnel with the entire cosmos concentrated in a brilliant disk at the end. Behind you and to the sides, only darkness. The entire universe has collapsed into a focal point, and at 99.9%, that circle compresses even further to only 9 degrees. All the galaxies, all the star clusters, all the light of the observable universe crushed into a disk the size of your extended fist. It is a spectacle that no image, no simulation can truly capture. The totality of the cosmos reduced to a brilliant point of infinite light. But that is not all. There is another, even more spectacular effect: relativistic Doppler shift. We are all familiar with the ordinary Doppler effect. It is what makes an ambulance siren sound higher-pitched when it approaches you and lower-pitched when it moves away. Sound is compressed when the source moves toward you and stretched when it moves away. Light experiences the same effect, but in terms of color instead of pitch. When a light source moves toward you, its light is shifted toward shorter wavelengths, from red toward orange, from orange toward yellow, from yellow toward blue, from blue toward violet. When it moves away, it is shifted in the opposite direction, toward red. At relativistic velocities, this effect becomes extreme. The stars in front of you, toward which you are moving, experience a massive blue shift. Their light is shifted toward higher frequencies. Red stars become orange, orange become yellow, yellow become white, then blue, then violet, and then, as you accelerate even faster, their light is shifted beyond the visible spectrum into the ultraviolet, X-rays, even gamma rays. Simultaneously, the stars behind you experience a massive redshift. Their light is stretched toward longer wavelengths. Blue stars become green, green become yellow, yellow become red, then infrared, then radio waves, until they finally disappear completely into the darkness, their light stretched to invisibility. At 99% of the speed of light, the stars in that concentrated disk in front of you do not look like ordinary stars at all. They shine with an intense, almost blinding blue-white light. Those that originally emitted red light now shine in yellow, the yellow ones in intense blue, the blue ones in violet or ultraviolet. The entire spectrum of every star has been shifted upward by an entire range, transforming the cosmic landscape into something completely unreal. And there is more. Because more light is being compressed in your direction of travel, the universe in front of you becomes dramatically brighter. It is an effect called relativistic beaming or relativistic searchlight effect. Imagine that each star is like a flashlight pointing in all directions. When you move toward it very fast, it is as if the flashlight suddenly focuses in your direction, concentrating all its light in a beam aimed directly at you. The result is that disk of concentrated stars in front of you is not only compressed and blue-shifted, but also intensified. It shines with a fierce glow that eclipses everything else. It is like looking directly into the sun, except it is not one sun, but billions of suns, all their lights mixed and amplified, creating a radiance that no unprotected eye could tolerate. Behind you, on the contrary, the universe darkens. The redshift causes the stars to dim. The relativistic anti-beaming distributes their light, making it less intense, and combined with the aberration that pushes them toward the edges of your vision, the result is an almost total darkness. It is as if you were leaving the universe behind, entering a void of absolute blackness. But wait, there is yet another effect we must consider: length, contraction. Just as time dilates when you move fast, space contracts. Distances in the direction of your motion become shorter. A 1-meter ruler aligned with your direction of travel would measure less than 1 meter from your perspective. At 99% of the speed of light, distances contract to approximately 14% of their original length. A journey of 100 light-years would take only 14 light-years according to your odometer. At 99.9%, the contraction is to 4.5%. 100 light-years becomes 4.5 light-years. This means that the universe in front of you is not only visually compressed, but is literally compressed from your perspective. The distances between stars shorten, galaxies flatten in the direction of your travel. Space itself compacts like an accordion, bringing everything closer to you. At the impossible limit of the speed of light, the contraction becomes infinite. All distances in your direction of travel are reduced to zero. The entire universe in front of you collapses into an infinitely thin plane. From the perspective of a photon, if it could have one, the distance between any 2 points in its direction of travel is exactly zero. The entire universe is a spatial singularity, with no extension in the direction of motion. Combine all these effects together: aberration, Doppler shift, beaming, length contraction. The result is a complete and total transformation of the cosmos. The known and recognizable universe disappears, replaced by a realm of extreme physics where space and time behave in ways that seem straight out of science fiction. Imagine the complete experience. You are in your ship, accelerating towards 99.9% of the speed of light. In front of you, the entire night sky has been reduced to a small, brilliant disk the size of a tennis ball held at arm's length. That disk glows with a fierce blue-white light, so intense that you have to protect your eyes. It is the light of billions of galaxies, all their frequencies shifted towards the blue, all their intensities amplified, all crushed into that single focal point. Around that disk, a ring of distorted stars, stretched into strange arcs by the curvature of light around your trajectory. And beyond that ring, almost total darkness. The universe behind you has disappeared into blackness, its light pulled beyond detection, its presence erased by the velocity of your motion. And all this is constantly changing. As you accelerate even a fraction of a percent faster, the disk compresses more, shines more intensely, becomes bluer. It is a dynamic spectacle of cosmic transformation, a visceral reminder that space and time are not absolute, but malleable, relative, dependent on the observer's motion. Some physicists have called this visual effect the relativistic travel glow. Others call it the cosmic headlight. but no name can truly capture the magnificence and alienation of the experience. It is the universe, revealing its true, relativistic nature, showing you that what we consider reality is only a perspective, one among infinite ways of seeing the cosmos, depending on how you move through space-time. And in this transformed landscape, you would travel toward your destination. Stars that would normally take decades or centuries to reach are now only years or months away due to length contraction. Time itself flows more slowly for you, making the journey seem even shorter. You could cross the galaxy in what would be only a few years for you, although millennia would pass for the rest of the universe. It is a very different vision of interstellar travel than what we see in popular movies, where ships simply move fast through a space that looks more or less normal. The reality of traveling near the speed of light is much stranger, much more alienating, and paradoxically, much more beautiful. The universe reveals itself not as a static stage, but as a dynamic entity that responds to your motion in deep and fundamental ways. But we have not yet explored the strangest perspective of all, that of light itself. What does a photon experience as it travels through the cosmos? The answer will lead us to one of the deepest mysteries of physics. There is a question that has fascinated physicists and philosophers since Einstein published his theory of special relativity. What does a photon experience? What is it like to be pure light, traveling eternally at 300,000 kilometers per second, with no mass, no charge, existing at the absolute limit of cosmic velocity? The answer is as profound as it is disconcerting. A photon experiences nothing at all. For a ray of light, time does not exist, space does not exist, distance does not exist. The entire observable universe, from the Big Bang to the end of time, is a single, timeless instant, with no spatial extension. Let me explain why this is so, because it is one of the most beautiful and disturbing concepts in all of physics. Let us recall time dilation. When an object moves faster, time flows more slowly for it, in comparison with slower objects. At 90% of the speed of light, time flows at approximately half speed. At 99%, at approximately 1/7 speed. At 99.9%, at approximately 1/22 speed. Do you see the pattern? As you approach the speed of light, time slows down more and more, not linearly, but exponentially. The slowing accelerates as you approach the limit. At the exact mathematical limit of the speed of light, time slows down infinitely. In other words, it stops completely. The time dilation factor becomes infinite. 1 second in the photon's frame of reference corresponds to an infinite time in the frame of reference of everything else. But wait, if 1 second for a photon is infinite time for us, then any finite amount of our time is exactly 0 seconds for the photon. 1 second is 0. 1 year is 0. 1 billion years is 0. From the photon's perspective, no time passes at all, regardless of how much time elapses in the outer universe. Now, let us consider length contraction. When an object moves very fast, the distances in its direction of motion contract. At 90% of the speed of light, distances contract to approximately 44%. At 99%, to approximately 14%. At 99.9%, to approximately 4.5%. Again, do you see the pattern? As you approach the speed of light, distances contract more and more towards zero. At the exact limit of the speed of light, the contraction becomes infinite. All distances in the direction of motion are reduced to exactly zero. From the perspective of a photon traveling through space, the distance between its point of emission and its point of absorption is literally zero. Not very small, not almost zero, exactly zero. The photon is simultaneously at its starting point and at its destination. The space between them has collapsed completely. Combine these two effects, zero time and zero distance. For a photon, the moment of its creation and the moment of its destruction are the same moment. The place where it is born and the place where it dies are the same place. There is no intermediate journey, because there is no intermediate. There is no duration, because there is no time. There is no trajectory, because there is no space to traverse. Consider a photon emitted by a star 1,000 light-years away. From our terrestrial perspective, that photon travels for 1,000 years through the void of space. It crosses the immeasurable distance between the stars, surviving intact through the darkness and the cold until it finally enters your eye and is absorbed by a rhodopsin molecule in your retina. 1,000 years of travel, 1,000 light-years of distance, a cosmic epic of endurance and velocity. But from the photon's perspective, the journey lasts exactly 0 seconds. The star and your retina are at the same point in space. The moment of emission and the moment of absorption are the same moment. The photon exists in an eternal present where the past and the future collapse into a single instant without duration. This is not metaphor or poetic exaggeration. It is the literal mathematical consequence of special relativity applied to the limit of the speed of light. Physicists say that photons do not have a valid frame of reference because the equations of relativity become singular infinite at the speed of light. But that technical jargon hides a deeper truth. Photons exist in a fundamentally different state of reality compared to everything that has mass. For us, beings of matter and mass, time is the most fundamental dimension of experience. Each moment flows to the next. Each second brings something new. Our existence is defined by the inexorable passage of time, from birth to death, from the past toward the future. But for a photon, time does not exist. There is only eternal existence, a present without beginning or end, or rather, a present where the beginning and the end are identical. The photon does not experience its journey because experience requires time, requires a sequence of moments, requires change, and for the photon, none of these things exist. It is as if the universe has two completely different modes of existence. The temporal mode, where we, and everything that has mass, live, and the timeless mode, where light and anything else that travels at the maximum speed exists. The temporal mode is the world of change, of causality, of narrative. It is where events happen in sequence, where the past influences the present and the present influences the future. It is the world of memory and anticipation, of history and progress. The timeless mode is the world of the eternal now, where all moments are simultaneous, where cause and effect collapse into identity. It is a world without narrative, because narrative requires time, without history, because history requires sequence, without change, because change requires before and after. And yet, these two modes are intimately connected. Light is the messenger between them. Every time you see something, photons traveling from the object to your eye are connecting you with that object across space-time. Those photons exist in their timeless mode, but they enable communication between entities that exist in the temporal mode. Moreover, light is what defines the boundary between these two modes. The speed of light is not arbitrary. It is the velocity at which information can propagate through space-time. It is the velocity of causality itself. Nothing can travel faster because that would violate causality, allowing effects to precede causes, breaking the logical structure of the universe. So, when a photon travels from a star to your eye, it is acting as a causal messenger. It is transporting information about the state of the star at the moment of emission to your eye at the moment of absorption. From your perspective, there is a delay. Light takes time to travel. But from the photon's perspective, the transfer is instantaneous. The star and your eye are connected directly, without temporal or spatial mediation. This leads to a profound philosophical question. Do photons really exist in the sense that we understand existence? Existence, as we experience it, is inherently linked to time. To exist is to persist through time, to change, to interact, to cause, and be affected. But photons do none of these things from their own perspective. They do not persist because no time elapses. They do not change because there is no sequence of states. They do not interact during their journey because their origin and destination are the same point. Some philosophers have suggested that photons exist in a different mode of being, something between existence and non-existence. From the perspective of the temporal universe, they clearly exist. We can measure them, detect them, use them, but from their own perspective, if they could have one, they experience no duration or extension, the two characteristics that we normally associate with existence. It is a mystery that touches the foundations of metaphysics and ontology. What does it mean to exist without time? What does it mean to be without becoming? But there is another, even deeper layer to this mystery. Photons not only exist in a timeless state, but they connect the past with the future in ways that challenge our ordinary understanding of causality. Consider this. When you look at a galaxy 1 billion light-years away, you are seeing light that was emitted 1 billion years ago according to your temporal frame. That galaxy might have changed dramatically or even ceased to exist in the intervening time. You are seeing the past. But from the perspective of the photons carrying that image to your eye, no time has passed. For them, the ancient galaxy and your modern retina are at the same temporal moment. The photon directly connects the distant past with the present, collapsing 1 billion years into 0 seconds. In a sense, the photon is preserving the past in an eternal present. The 1 billion-year-old galaxy has not disappeared into the past from the photon's perspective. It still exists in the same eternal moment that also includes your present observation. This suggests a very different view of the universe than our ordinary intuition. We normally think of time as a river that flows, carrying events from the present into the past, leaving them behind forever. The past has ceased to exist. The future does not yet exist. Only the present is real. But the photon's perspective suggests something different, that all moments of time exist simultaneously in a four-dimensional structure called the block universe spacetime. The past has not ceased to exist. It is simply in a different location, in the temporal dimension. The future already exists. We simply have not yet reached it on our trajectory through time. From this perspective, the universe is like a complete film where all the scenes exist simultaneously on the film reel, even though we experience them sequentially when we project it. Photons, traveling at the speed of light, experience the complete reel as a single timeless image, while we, moving much more slowly through spacetime, experience each frame sequentially. This is the view of the universe that Einstein himself came to embrace. After the death of his close friend, Michel Besso, Einstein wrote to the family, "Michel has departed from this strange world a little ahead of me. That means nothing. For us convinced physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." For Einstein, who had thought more deeply than anyone about the nature of space and time, relativity suggested that all moments are equally real, that the flow of time is a subjective perspective, and that the universe viewed from outside time is an eternal, immutable structure where all events coexist. And photons, traveling at the boundary between the temporal and the timeless modes, are the messengers that connect these two visions of reality. They are simultaneously part of our temporal world, carriers of causal information, and part of the timeless world of the eternal present. When a photon from the sun enters your eye, it is directly connecting the sun's core with your retina across a timeless bridge. From your perspective, that photon traveled for 8 minutes. But from the photon's perspective, if it could have one, the heart of the sun and your eye are at the same place and moment. There is no separation, no travel, no duration. It is a form of existence so far removed from our experience that we can barely conceive of it. And yet, it is fundamental to the universe. Light is perhaps the most ubiquitous thing in the cosmos. It fills all space, connects all things, enables all observation, and exists in this impossible state of timelessness and non-distance. If you could, for an impossible instant, experience the universe as a photon experiences it, you would see the entire history of the cosmos collapsed into a single moment. The Big Bang and the end of the universe would be simultaneous. Every star that ever shone, and every star that ever will shine, would exist in the same eternal instant. All space would be reduced to a single point with no extension. You would be omnipresent and omnitemporal, not because you were in all places and at all times, but because all places and all times would have collapsed into a single here-now. But, of course, this thought experiment is impossible. Only massless things can reach the speed of light and experience this timeless perspective. Everything that has mass, including us, is condemned to move more slowly, to exist in the flow of time, to experience the universe sequentially, rather than simultaneously. And perhaps that is something beautiful. Perhaps the flow of time, the narrative of existence, the journey from the past to the future is a gift rather than a limitation. It allows us to experience change, growth, surprise, discovery. It allows us to have stories instead of just states. It allows us to become instead of just exist. The photons, in their perfect timelessness, never change, never learn, never become. They simply are eternally, in a present without end. We, in our temporal existence, are constantly becoming, transforming, evolving, from moment to moment. And yet, we envy the speed of light. We dream of reaching it, of crossing the vast distances of space in an instant. But perhaps what we truly envy is not the speed, but the timelessness, the escape from the inexorable flow of time toward aging and death. But if we could reach it, if we could become light, we would cease to exist in the sense we know. There would be no experience, no consciousness, no you. Only an eternal instant, without content or duration, an existence so different from life that it would be indistinguishable from non-existence. The limit of the speed of light isn't merely a physical barrier. It is the boundary between two fundamentally different modes of being, the temporal mode of matter and the atemporal mode of light. And we, beings of matter, are perpetually on the temporal side of that barrier, peering across it into a realm we can never enter and can barely comprehend. Up until now, we have discussed abstract physics, timeless photons, and transformed universes. But now, we must confront a more visceral and disturbing question. What would happen to an actual human body if it could somehow approach the speed of light? Not just the time you would experience or the sights you would see, but the flesh and blood, the molecules and atoms that compose you. The answer is unsettling. Traveling at relativistic speeds would not be simply uncomfortable or dangerous. It would be incompatible with biological existence in fundamental and absolute ways. Your body, optimized by millions of years of evolution to exist in a relatively tranquil environment on the surface of a planet, would face forces that would tear it apart atom by atom. Let us begin with the most obvious problem: radiation. Space is not empty. Even in the most remote regions of the interstellar void, a tenuous environment of gas exists, approximately 1 atom of hydrogen per cubic centimeter on average. It sounds sparse, and it is. It is a better vacuum than anything we can create in terrestrial laboratories. At normal speeds, these scattered particles are completely harmless. Your spacecraft would slice through them without even noticing. But at relativistic speeds, these harmless atoms are transformed into deadly projectiles. Recall the relativistic Doppler shift we discussed earlier. When you move very fast toward a source of radiation, that radiation is shifted to higher frequencies, toward more energy. A photon of visible light becomes ultraviolet, then X-rays, then gamma rays. The same principle applies to atoms. When you move at 99% of the speed of light, every hydrogen atom you collide with hits you with the kinetic energy of a particle moving at 99% of the speed of light relative to you. The collision energy is proportional to the square of the Lorentz factor, which at these speeds is approximately 7. A single hydrogen atom striking your ship at this velocity would carry approximately 10 to the negative 9 joules of energy. It sounds small, but remember, there is approximately 1 atom per cubic centimeter. If your ship has a frontal area of, say, 10 square meters, you would be colliding with approximately 10 to the 9 atoms per second. That is approximately 1 watt of power deposited on the front surface of your ship as high-energy radiation. 1 watt doesn't sound bad, does it? But that is only at 99%. The collision energy increases dramatically as you approach closer to the speed of light. At 99.9%, you are receiving approximately 50 watts of radiation. At 99.99%, 500 watts. At 99.99%, 5,000 watts. And this is not ordinary radiation. At these velocities, the hydrogen atoms colliding with your ship behave like ultra-high energy cosmic rays. Each collision creates a cascade of secondary particles: pions, muons, electrons, positrons, gamma rays. It is as if your ship were being bombarded by a natural particle accelerator. The radiation would penetrate deeply into any shielding material. Ordinary cosmic rays can slice through meters of lead. These would be far more energetic. They would pierce your ship's hull, pass through any shielding you could carry, and deposit their energy directly into your body. At the cellular level, this radiation would be devastating. Every high-energy particle slicing through your body would break DNA chains, destroy protein molecules, and ionize atoms, creating toxic free radicals. A single particle could damage thousands of cells along its track. At sufficiently high speeds, the radiation dose you would receive would be lethal in a matter of seconds or minutes. Not lethal in the sense of you will eventually die of cancer. Lethal in the sense that your cells are being destroyed faster than they can repair themselves. Your tissues are disintegrating. You are experiencing massive necrosis throughout your body. And that is just from the relatively empty interstellar medium. Should you pass through a denser gas cloud or near a star where the particle density is higher, the radiation would increase proportionally. It will be like flying through a nuclear furnace. But radiation is only the beginning of your problems. There is something even more fundamental: relativistic mass increase. Recall that as you accelerate, your effective mass increases. At 99% of the speed of light, your mass is approximately 7 times your rest mass. At 99.9%, approximately 22 times greater. This poses an extraordinary problem for biology. Your body is structured to function with a specific mass. Your heart is designed to pump blood of a certain density against a certain gravity. Your muscles are calibrated to move bones of a certain mass. Your cells are built to operate in an environment with certain physical properties. But if your mass increases 20 times, everything changes. Your blood becomes 20 times heavier. Your heart would have to generate 20 times more force to pump it. Your bones would experience 20 times more stress from any acceleration or external force. It would be as if you suddenly experienced a gravity 20 times stronger than on Earth. No human body could function under such conditions. Your heart could not pump blood against that increased mass. Your skeleton would crush under its own augmented weight. Your organs would collapse. You would become paralyzed and immobile, unable to breathe, to move, possibly even to think if the mass increase affects the electrochemical processes in your brain. And that assumes you somehow reached this velocity gradually. If you attempted to accelerate from rest to relativistic speeds over any reasonable period of time, the acceleration forces alone would kill you long before you reached dangerous velocities. Humans can tolerate approximately 5 times Earth's gravity for short periods before losing consciousness due to blood draining from their brain. Trained fighter pilots in special suits can tolerate perhaps 9 times gravity for brief moments. Beyond that, the forces simply exceed what the human body can bear. Blood vessels rupture, organs are damaged, bones fracture. To accelerate up to 99% of the speed of light at an acceleration of, say, 10 times, Earth's gravity, already quite uncomfortable, would take approximately 11 months. And that is an acceleration that would likely kill or permanently incapacitate anyone who experienced it for that long. If you wanted to accelerate more gently, say, at the acceleration of Earth's gravity that we constantly experience, it would take almost 1 year to reach 99% of the speed of light. And for that entire time, you would be exposed to ever-increasing levels of radiation as your speed mounted. But there is another problem, even more subtle and fundamental: length contraction. Special relativity states that objects contract in the direction of their motion. But what does this mean for a human body composed of trillions of cells, each with its own complex molecular structure? Your cells are carefully organized into tissues and organs with specific geometries. Your heart has a particular shape. Your brain has a precise 3-dimensional structure where neural connections are arranged in specific patterns. All of this depends on the distances between parts remaining consistent, but length contraction is not uniform in all directions. It only contracts in the direction of motion. So, if you were traveling at relativistic speeds straight ahead, your body would be compressed in that direction, but remain unchanged in the perpendicular directions. How would your organs function when they are geometrically distorted? Could protein molecules maintain their functional shapes when the distances between atoms change in one direction, but not in others? Could cells maintain their structural integrity? The answer is probably no. Biochemistry depends critically on precise molecular geometries. Enzymes work because they have specific shapes that fit their substrates, like keys in locks. Cell membranes function because lipid molecules assemble into bilayer structures of specific geometries. Ribosomes synthesize proteins because their subunits are spatially organized in precise ways. If you distort all these geometries in one dimension while leaving them unchanged in the other two, it is hard to see how they could continue to function. It would be like taking a complicated machine and compressing every component in one direction. Even if the individual components didn't break, their interactions and relationships would change in ways that would likely shatter the system's functionality. Of course, from your own perspective traveling in the ship, you would notice no contraction. Relativity says that you always measure yourself as having your normal length and shape. It is only from the perspective of someone in relative rest that you appear contracted. But here is the problem. Your molecules and atoms do not know which frame of reference they are in. The electromagnetic forces that hold atoms and molecules together act according to the laws of physics, which are the same in all reference frames. So, how do they behave when different parts of the system are in different states of relative motion? This is a profound question that touches the fundamentals of how relativity and quantum mechanics interact. The general answer is that physics works correctly in all reference frames, but situations where you have extreme accelerations or velocity gradients within a complex system can lead to stresses and forces the system is not designed to handle. In the case of a human body, the conclusion is clear. We are not built to exist at relativistic speeds. Our biological structures depend on specific geometries, specific densities, specific chemical reaction rates, all calibrated for the relatively tranquil environment of a planet's surface moving at everyday velocities. Introduce relativistic velocities, and all these parameters change. Masses increase, lengths contract, time slows down, which means chemical processes occur at different rates compared to the outside world, and the ambient radiation transforms into a lethal storm of high-energy particles. It is not just that we lack the technology to shield a human traveling at these speeds. It is that biology itself seems fundamentally incompatible with the extreme physics near the universe's speed limit. This suggests something profound, that there are different regimes of physics, different domains of the universe, where different types of structures and systems can exist. At low velocities and moderate energies, biological complexity can flourish. Cells, organisms, ecosystems, all the intricate structures of life are possible. But at relativistic speeds and extreme energies, only the simplest structures can survive. Individual particles like protons and electrons routinely travel at near-light speeds in cosmic rays. Simple atomic nuclei can be accelerated to these speeds in particle accelerators, but nothing complex, nothing structured, nothing living can exist in this regime. It is as if the universe has different zones, different habitats, each hospitable to different types of existence. The low-speed zone where we live is where complexity flourishes. The high-speed zone near the light limit is where only simplicity can survive. And at the limit itself, at the exact speed of light, only things with no internal structure whatsoever can exist. Photons, elementary particles, with no parts, no complexity, no information beyond their energy and direction. Perhaps this is the most profound reason why we can never reach the speed of light. It is not just that it would require infinite energy, though that is true. It is not just that time would stop, though that is also true. It is that the type of complex, structured existence we call life, we call mind, we call identity, is fundamentally incompatible with the mode of existence that occurs at the speed of light. We are creatures of the low-speed regime. Our bodies, our minds, our entire lives are structured around the physics of slow motion, gradual change, and orderly causality. We are inhabitants of the temporal world, where time flows, where change happens, where stories unfold. The speed of light marks the boundary of our domain, not just technologically, but ontologically. It is the boundary between the existence we can experience and the existence we can only contemplate from afar, with awe and some dread. And yet, there is beauty in this limit. It means that the universe has structure, it has domains, it has limits. Not everything is possible everywhere, Different regions of the space of physical possibilities are hospitable to different kinds of existence, and we inhabit one of those domains, a special corner of the universe where complexity can flourish, where life can emerge, where consciousness can awaken and contemplate the cosmos. Although no human has ever traveled at near-light speeds, and probably never will, the universe is full of natural travelers that routinely achieve these extreme velocities. They are the messengers of the cosmos, particles accelerated by violent astrophysical processes to energies that defy imagination. And by studying them, we can learn about the extreme physics near the universe's speed limit. The most ubiquitous of these travelers are cosmic rays, charged particles, primarily protons, that constantly bombard Earth from all directions in space. They were discovered more than 100 years ago by Victor Hess, who flew in hot air balloons with electroscopes and found that the radiation increased with altitude rather than decreasing, indicating it was coming from outer space, not Earth. For decades afterward, physicists assumed that cosmic rays were some kind of radiation, hence the name. But eventually, it was discovered that they were particles, primarily protons, traveling at incredible speeds, and not just fast, but relativistically fast, approaching the universe's speed limit. Ordinary cosmic rays, the ones constantly streaming into Earth's atmosphere, typically travel at 99% of the speed of light, or faster. Every second, approximately 1,000 cosmic rays pass through your body. Most are absorbed or scattered by the atmosphere before reaching ground level, but some make it all the way down, and a few pass straight through you. These are the mid-range cosmic travelers, fast but not extreme by the universe's standards. They likely originate from supernovae, stars that exploded in our galaxy, accelerating particles to tremendous velocities in their shock waves. But there are far more energetic, far faster cosmic rays that occasionally arrive. They are called ultra-high energy cosmic rays, and they are some of the most mysterious and extreme phenomena in astrophysics. The highest energy cosmic ray ever detected was observed on October 15, 1991, by the Fly's Eye experiment in Utah. It was a single proton, traveling at 99.99999999% of the speed of light. Let me repeat that for emphasis. 99.219% of the speed of light. It is so close to the limit that the difference between its speed and the speed of light is less than the speed at which a snail crawls. The energy of this proton was approximately 316 exa-electronvolts, or 51 joules. That doesn't sound like much until you realize that is the energy of a baseball thrown at approximately 92 kilometers per hour, all contained in a single subatomic particle, a single proton, with the kinetic energy of a macroscopic object. It is astonishing. Scientists nicknamed it the "Oh my God" particle because of the reaction it provoked when its energy was calculated. It violated all the theoretical limits that were thought to exist for cosmic ray energies. It was so energetic that it shouldn't exist according to our understanding of astrophysics. You see, there is a theoretical limit called the GZK limit, named after Greisen, Zatsepin, and Kuzmin, who predicted it in 1966. It states that protons with energies above a certain threshold, approximately 50 exa-electronvolts, should interact with the cosmic microwave background radiation that pervades all space. This radiation, a remnant of the Big Bang, consists of very low-energy photons, mostly in the microwave range. To us, moving slowly, these photons are completely harmless, virtually undetectable, except with sensitive instruments. But to a proton, moving at 99.219% of the speed of light, these low-energy photons appear blue-shifted to gamma-ray energies due to the extreme relativistic Doppler shift. From the proton's perspective, it is being bombarded by intense gamma-ray radiation. When an ultra-high energy proton collides with one of these photons, it can produce a pion, a subatomic particle. This process robs energy from the proton, slowing it down. And because the cosmic microwave background radiation is everywhere, an ultra-high energy proton should collide with these photons repeatedly as it travels through space. The calculations show that a proton with energy above the GZK limit should lose most of its energy within approximately 160 million light-years of travel. This means that any ultra-high energy cosmic ray we detect on Earth must have originated within approximately 160 million light-years. Otherwise, it would have been slowed down below the GZK threshold. The problem is that there are no obvious sources for such particles within this distance. The most likely sources, such as active galactic nuclei or gamma-ray bursts, are almost all much farther away. So, where do these ultra-high energy cosmic rays come from? It is one of the great unsolved mysteries of astrophysics. Perhaps the particles are not protons, but heavier nuclei that could travel farther before being stopped. Perhaps there is new physics we do not yet understand that allows the particles to circumvent the GZK limit. Perhaps there are nearby sources we have yet to identify. But regardless of their origin, these particles are natural laboratories for extreme physics. They reach energies far higher than anything we can produce in terrestrial particle accelerators. The Large Hadron Collider, the most powerful particle accelerator ever built, accelerates protons to approximately 7 tera-electron volts, which sounds impressive until you realize that is approximately 45 million times less energetic than the oh my god particle. When these ultra-high energy cosmic rays strike Earth's upper atmosphere, they create spectacular cascades of secondary particles. The incoming proton collides with an atmospheric nucleus, creating an explosion of pions, kaons, and other exotic particles. These secondary particles, in turn, decay or collide with other nuclei, creating more particles. The result is an extensive air shower that can contain billions of particles spread over square kilometers by the time they reach the ground. Detectors on the surface can map these showers by measuring where and when the particles arrive. From this pattern, scientists can reconstruct the direction, energy, and possibly the type of the original particle. It is like forensic archaeology, reconstructing the original event from its scattered remnants. But cosmic rays are not the only natural travelers at extreme velocities. Particle accelerators can also accelerate particles to relativistic speeds, albeit with lower total energies than the most extreme cosmic rays. In the Large Hadron Collider, LHC, protons circulate in a 27-kilometer tunnel of circumference, accelerated by intense electromagnetic fields. They reach speeds of 99.999991% of the speed of light. They are so close to the limit that they complete 11,245 laps per second, each lap taking approximately 89 microseconds. At this speed, a proton in the LHC experiences significant time dilation. Its internal clock runs approximately 7,000 times slower than laboratory time. If a proton could carry a clock, that clock would advance by 1 second for every 2 hours of laboratory time. This time dilation has practical consequences. Some of the particles created in collisions at the LHC are inherently unstable and decay quickly. For example, the B meson, a particle composed of a bottom quark, has a half-life of approximately 1.5 picoseconds in its own rest frame. That is 1/millionth of a second. In 1.5 picoseconds, light travels approximately half a millimeter. So, you would normally expect a B meson to travel 0.5 millimeter before decaying, but when it is created, moving at near light speeds in the LHC, its life is extended by time dilation. From the laboratory's perspective, it lives longer and travels farther before decaying, perhaps several centimeters instead of 0.5 millimeter. Particle physicists routinely account for these relativistic effects in their calculations. Special relativity is not a theoretical curiosity for them. It is a practical necessity for correctly interpreting their data. If they ignored time dilation, their calculations of particle masses, half-lives, and other parameters would be completely wrong. There is another natural traveler we must mention: neutrinos. These ghostly particles, with no electric charge and almost zero mass, travel at speeds so close to light that for decades it was thought they might have no mass at all. Neutrinos are created in nuclear reactions, such as the fusion occurring in the Sun's core. Every second, approximately 65 billion solar neutrinos pass through every square centimeter of your body. They travel at speeds greater than 99.99% of the speed of light. But the extraordinary thing about neutrinos is not just their speed, but their indifference to the rest of the universe. Unlike charged protons in cosmic rays, which interact strongly with matter and are stopped by the atmosphere, neutrinos interact with almost nothing. They can traverse the entire planet Earth without being absorbed. In fact, the majority of neutrinos passing through, you have traversed the entire planet, having entered from the opposite side. This ghostly nature means that neutrinos are perfect messengers from the deep cosmos. While light can be absorbed or scattered by dust and gas, and charged particles are deflected by magnetic fields, neutrinos travel in perfectly straight lines from their source to us, undisturbed by anything in between. In 1987, when a star exploded as a supernova in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, neutrino detectors on Earth caught a handful of neutrinos from the explosion. Only 19 neutrinos in total, out of the countless trillions that passed through Earth. But those 19 were enough to confirm our theories about how supernovae work, and to demonstrate that neutrinos can travel through intergalactic space without loss. More recently, in 2010, physicists achieved something remarkable. They directly measured the difference between the speed of light and the speed of neutrinos. They created neutrinos at CERN in Switzerland and detected them at Gran Sasso in Italy, 730 kilometers away. The neutrinos arrived approximately 60 nanoseconds before light would arrive, traveling the same distance. Initially, this caused great excitement because it seemed that the neutrinos were traveling faster than light, which would violate special relativity. But after careful investigation, it was discovered that there was an error in the synchronization of the clocks due to a loose fiber optic connection. When the error was corrected, it turned out that the neutrinos were traveling exactly at the speed that relativity predicts, slightly slower than light, by an amount consistent with their tiny mass. This episode illustrates something important. Special relativity has been tested again and again in increasingly extreme circumstances, and it has always passed the test. It is not just a beautiful theory. It is an accurate description of how the universe truly works. All these natural travelers, from cosmic rays to neutrinos to particles and accelerators, are constantly confirming the predictions of relativity, time dilation, length contraction, mass increase, the equivalence of energy and mass. All these bizarre consequences of special relativity are routinely observed and must be accounted for in practical experiments. The universe is a much larger and more powerful laboratory than anything we can build, and it is telling us through these natural travelers that Einstein was right. The speed of light is a fundamental limit, and the physics near that limit is exactly as strange as relativity predicts. But these travelers also tell us something else, that the universe contains processes of extraordinary energies that we can barely imagine. The sources that accelerate cosmic rays to energies of 300 exa-electron volts must be cataclysmically powerful. We are talking about supernova explosions, black hole collisions, quasar jets, events so violent that they release more energy in seconds than our Sun will emit in its entire 10 billion year lifetime. The cosmos is not a tranquil place. It is filled with violence, energy, and extremes that defy comprehension. And in the midst of all this, individual particles are accelerated to velocities so close to light that they experience the universe in fundamentally different ways than we do. For these particles, time flows differently. Distances are different. Indeed, the universe itself has a different geometry. They are visitors from the relativistic regime, a domain of physics that we can never visit corporally, but which we can study through its messengers. And by doing so, we learn not only about extreme physics, but about the limits of the possible. We learn where the edges of the space of physical possibilities lie, what kinds of processes the universe can support, what energies and velocities are achievable. It is a reminder that even though we are confined to our small corner of the universe, moving slowly on the surface of our planet, we are part of a much larger, more extreme cosmos. And that cosmos sends us messengers, travelers who have experienced physics we will never experience, bringing news from the boundaries of reality. We have explored why we cannot reach the speed of light. We have seen how it would require infinite energy, how time would stop, how our bodies would be destroyed by radiation and extreme forces. The limit seems absolute, insurmountable, a fundamental law of the universe, as unmovable as any other. But the human mind is tenacious. Confronted with the impossible, it immediately begins to look for shortcuts, loopholes, ways to bypass the rules without directly violating them. And physicists, being human after all, have thought deeply about whether there might be ways to travel faster than light, without actually moving faster than light through space. It sounds paradoxical, but the distinction is important. Special relativity says that nothing can move through space faster than light, but it says nothing about space itself moving, or about shortcuts through space, or about other dimensions. These possibilities have given rise to some of the most fascinating and controversial speculations in theoretical physics. Let us begin with the most famous, wormholes. A wormhole, or Einstein-Rosen bridge, as it is technically called, is a mathematical solution to Einstein's equations of general relativity. It is a hypothetical structure in spacetime that connects two distant locations through a shortcut. Imagine space as a sheet of paper. Normally, to travel from one point to another on the paper, you must move along the surface. But if you could fold the paper and punch a hole through it, you could create a shortcut that is much shorter than the path over the surface. That is essentially what a wormhole is, a tunnel through spacetime that connects two distant points. If a wormhole existed between Earth and a star 1,000 light-years away, you could theoretically enter one end, travel through the wormhole, and emerge from the other end, having crossed 1,000 light-years in, say, a few minutes or days of your own time. Crucially, at no point would you travel faster than light through space. Inside the wormhole, you would move at normal, subluminal speeds. It is just that the geometry of spacetime has been distorted in such a way that the distance you need to travel is much shorter than the exterior distance between the 2 points. It sounds like science fiction, and indeed, wormholes are a staple of science fiction movies and novels. But mathematically, they are valid solutions to Einstein's equations. The problem is that they are extremely exotic solutions that require conditions that probably do not exist in nature. First, a traversable wormhole, one you could travel through from one side to the other, requires something called exotic matter. This is not ordinary matter composed of atoms. It is matter with negative energy density, meaning it exerts negative pressure, pushing outward instead of inward. In ordinary physics, all known matter has positive energy density. Exotic matter with negative energy density would violate what is called the weak energy condition, an assumption that underlies much of our understanding of how gravity works. There is no evidence that such matter exists in macroscopic quantities, although there are some exotic quantum effects, such as the Casimir effect, that produce small amounts of negative energy under special conditions. To hold open a wormhole large enough for a spaceship to pass through, you would need astronomical quantities of this exotic matter distributed in very specific ways. Estimates vary, but some suggest you would need the negative mass equivalent of a star or more. We do not only not know how to create such matter, but we do not even know if it can exist in the required quantities. Second, even if you could create a wormhole, it would likely be unstable. The slightest perturbations, even a single photon attempting to pass through, could cause the wormhole to collapse catastrophically and almost instantaneously. Holding it open would require extraordinarily precise control and stabilization. Third, creating a wormhole in the first place would require manipulating the structure of space-time at energy scales that are completely out of our reach. We are talking about energies comparable to those of the Big Bang, concentrated in specific regions of space. It is not just that we lack the technology, it is that we do not even have a clear concept of what kind of technology could do this. And there is one subtle additional problem. If wormholes could exist and be traversable, they could potentially be used to create time machines, allowing travel backward in time. This leads to causal paradoxes, like the famous grandfather paradox. What happens if you travel to the past and prevent your grandparents from meeting? Some physicists argue that the universe must have some unknown mechanism, a chronology protection, that prevents the formation of causal time loops. Perhaps wormholes simply cannot exist in configurations that would allow time travel. Perhaps they automatically collapse before they can be used in this way. But these are speculations, not proven theories. The conclusion is that while wormholes are mathematically possible according to general relativity, their physical existence is highly speculative. They are a theoretical, maybe rather than a practical, yes. Another speculative idea is the warp drive, popularized by science fiction but based on real physics, proposed by physicist Miguel Alcubierre in 1994. The idea is to create a bubble in space-time, where the space in front of a ship contracts and the space behind expands. The ship itself remains stationary within the bubble, but the bubble moves through space, potentially faster than light. Again, the idea is that you are not violating special relativity, because you are not moving faster than light through space. Instead, space itself is moving, carrying you with it. It is like standing on a conveyor belt that is moving faster than you can run. You are not running faster than your top speed, but you reach your destination faster because the floor beneath you is moving. The Alcubierre warp drive is mathematically consistent with general relativity. The equations work, but like wormholes, it requires exotic matter with negative energy density, and the required quantities are truly astronomical. Initial estimates suggested you would need the mass-energy equivalent of multiple times the mass of the observable universe. Later research has reduced this number somewhat, but it remains ridiculously large. Furthermore, there are practical problems. How do you create the warp bubble in the first place? You would have to manipulate space-time from outside the bubble, but once you are inside, you cannot control it, because any signal you send cannot propagate faster than light, and therefore cannot exit the bubble. It is like being in a boat without oars or an engine, waiting for the current to carry you where you want to go. There are also concerns about what would happen to any matter or radiation you encounter on your path. Some calculations suggest that radiation would accumulate at the front of the warp bubble, creating an intense radiation beam that would incinerate your destination when you finally stopped the bubble. Not ideal if you are trying to visit another star. Another speculative idea involves tachyons, hypothetical particles that travel faster than light. Special relativity does not absolutely forbid the existence of such particles. What it forbids is accelerating a particle from below the speed of light to above it. But, mathematically, you could have particles that always travel faster than light, just as we have photons that always travel exactly at the speed of light. The problem with tachyons is that they would have very strange properties. Their mass would be imaginary, in the mathematical sense of involving the square root of a negative number. They would lose energy as they accelerate and gain energy as they decelerate, and they would have strange causal effects, potentially allowing communication backward in time. Despite extensive searches, tachyons have never been detected. Most physicists believe they do not exist, and that their mathematical existence in the equations of relativity is just a curiosity, without physical meaning, but we cannot absolutely rule them out. Then there is cosmological expansion. We know from astronomical observations that the universe itself is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they move. In fact, sufficiently distant galaxies are moving away from us faster than the speed of light. How is this possible without violating relativity? The answer is that the galaxies are not moving through space faster than light. Instead, new space is being created between us and them. It is a subtle but important distinction. Special relativity limits movement through space, not the expansion of space itself. This has led some people to speculate. If space can expand faster than light, could we harness this expansion somehow? Could we create a region of space that expands behind us and contracts in front of us, effectively surfing the cosmic expansion? This idea overlaps with the concept of the warp drive. In fact, the Alcubierre warp drive is essentially a localized version of cosmological expansion, but the problems are the same. It requires exotic matter, monumental energies, and control over space-time that is completely outside our current or foreseeable capabilities. There is another, more exotic possibility: additional dimensions. String theory, a candidate for a unified theory of all physics, suggests that the universe could have more than the three spatial dimensions we experience. There could be additional spatial dimensions curled up on microscopic scales, too small to detect directly. If such dimensions exist, could we somehow access them? Could we step out of our usual 3 dimensions, travel through an extra dimension, and step back in at a different location? It would be like a 2-dimensional cartoon character living on a sheet of paper, discovering that it can step off the paper, move through the 3rd dimension, and re-enter the paper at a different location. It is a fascinating idea, but completely speculative. We have no evidence that extra dimensions exist, let alone that they are large enough or accessible enough to allow travel. And if they did exist, the energies required to access them would likely be on the Planck scale, energies so high that they would be unattainable with any conceivable technology. All these ideas, wormholes, warp drives, tachyons, extra dimensions, are fascinating as theoretical exercises. They tell us something about the structure of physical laws, about what is mathematically possible within the framework of our theories, but none of them offer a practical path, even in principle, toward faster than light travel. The reality is that we are limited by the universe's speed limit, not because our technology is inadequate, though it certainly is, but because the fundamental laws of physics seem to prohibit this type of travel. This means that interstellar travel, if it ever happens, will be slow by cosmic standards. Even traveling at a significant percentage of the speed of light, say 50%, it would take more than 8 years to reach the nearest star. Reaching the center of our galaxy would take more than 50,000 years, and other galaxies are completely out of reach for any period of time comparable to human civilizations. Unless we discover new physics that goes beyond general relativity and quantum mechanics, we are confined to our cosmic neighborhood. The Milky Way is our home. Even fully exploring it would take millions of years with subluminal technology. This may sound depressing, a cruel limitation imposed by the universe, but there is also a certain beauty in it. It means that the universe has structure, it has rules, it has limits. Not everything is possible. Some things are forbidden, not by lack of imagination or technology, but by the fundamental laws of reality. And these limitations shape how the universe evolves. If faster-than-light travel were easy, the universe would be a very different place. Civilizations could expand limitlessly. Information could propagate instantaneously. Causality could be violated. Instead, we live in a universe where information travels at a finite speed, where cause always precedes effect, where distances mean something. It is a universe where isolation is the norm. Every star, every galaxy, exists in its own causal bubble, separated from the others by vast oceans of space and time. The light from distant stars shows us their past, not their present. We are looking back in time through the telescope, seeing the universe not as it is, but as it was. And yet, within these limitations, there is room for wonder, exploration, and discovery. Our own solar system remains mostly unexplored. Our galaxy contains hundreds of billions of stars we have never visited. There are enough mysteries in our cosmic neighborhood to keep humanity occupied for millennia. Perhaps the universe's speed limit is not a prison, but a reminder that we are part of this cosmos, subject to its laws, shaped by its limits. A reminder that the impossible exists, and that recognizing it is the first step toward wisdom. We have reached the end of our impossible journey toward the speed of light. We have explored the physics, the mathematics, the practical and theoretical consequences of approaching that ultimate limit of the universe. And perhaps along the way, you have felt a certain frustration. Why does this limit exist? Why does the universe deny us the ability to travel as fast as we want, to cross cosmic distances in an instant, to explore the stars as we explore our own planet? But there is another way to view this limit, not as an arbitrary or cruel restriction, but as a fundamental and necessary feature of a universe that can contain structure, complexity, life, and mind. The limit of the speed of light is not a flaw of the cosmos. It is, in many ways, a gift. Allow me to explain why. First, the speed of light is what connects space with time. In Einstein's relativity, space and time are not separate entities, but aspects of a single unified structure, space-time. And the speed of light is the constant that defines how these two dimensions relate. When you measure distances in meters and time in seconds, the speed of light appears as 300,000 kilometers per second, a number that seems arbitrary. But if you measure distance in light years and time in years, the speed of light is simply one light year per year, is the natural unit of velocity in the universe. This unit defines the structure of space-time. It says that moving 1 light year through space is equivalent, in some deep sense, to moving 1 year through time. Space and time are interchangeable, related by this fundamental conversion factor. Without this speed limit, without this connection between space and time, the universe would be fundamentally different. Space and time might be completely independent, disconnected, unrelated to each other. And in such a universe, many of the properties we take for granted might not exist. Second, the speed of light is the velocity of causality. It is the maximum speed at which information can propagate, the speed at which causes can produce effects. If you could send information faster than light, you could violate causality, creating situations where effects precede causes. Imagine you can send a message faster than light to a spaceship moving away from you. From your perspective, the message arrives after you sent it. But due to the relativity of simultaneity, from the perspective of someone moving in a certain way, your message could arrive before you sent it. They could send you a reply that would arrive before you sent the original message. This would create causal loops, time paradoxes, situations where the future affects the past. The logical structure of the universe would break down. You could not rely on causes producing effects predictably. Science, which relies on causality, would be impossible. The speed of light limit prevents this. It ensures that causes always precede effects, that the past is fixed and the future is open, that time has a direction. This causal structure is what makes possible the existence of complex systems that process information, systems like brains and computers. Without consistent causality, thought itself would be impossible. Third, the speed limit creates structure in the universe. Because information cannot travel instantaneously, different regions of space can develop independently, at least temporarily. This allows for diversity, variation, and the evolution of different solutions to the challenges of existence. If information could propagate instantaneously, the entire universe would be in instantaneous contact with everything else. Perturbations in one region would be felt immediately everywhere. There would be no isolation, no independence, no possibility for different regions to explore different possibilities. Instead, we live in a universe where every region is enveloped in its own causal horizon, defined by how far light can travel since the Big Bang. This creates a rich structure where different parts of the universe have different histories, different compositions, and different destinies. It is a universe of variety rather than uniformity. Fourth, special relativity with its speed limit is what makes the equivalence between mass and energy possible. The famous equation, $E equals mc circumflex, $2, only makes sense in a universe where the speed of light is a fundamental limit. This equivalence is what allows stars to shine, nuclear fusion to release energy, and the sun to sustain life on Earth. Without the relativistic connection between mass and energy, the universe would be a cold, dark place. Stars could not convert mass into energy through nuclear fusion. There would be no long-term energy source to sustain life. The cosmos would be radically different and inhospitable. Fifth, the speed limit is what makes light special. Photons, traveling at this limit, are the messengers of the universe. They connect different regions of space-time, transport information across the vacuum, and allow us to see and understand the cosmos. If there were no speed limit, if all velocities were possible, light would not have a special status. It would be just another form of radiation among many. Instead, light defines the causal structure of space-time. It is the limit, the mediator, the messenger. It has a fundamental role in physics that it would not have without the speed limit. Sixth, and perhaps most profoundly, the speed limit preserves the mystery of the universe. It ensures that distant regions of the cosmos remain distant, that not everything is immediately accessible, that there are always horizons beyond which we cannot easily see or reach. In a universe without a speed limit, everything would eventually be accessible. We could explore every corner, catalogue every star, and map every galaxy. The cosmos would become a finite, knowable place, without lasting mysteries. But in our universe, with its speed limit, there is always more beyond the horizon. There are always galaxies that are so far away that their light has not yet reached us. There are always regions of space-time that are causally disconnected from us, existing in their own independent reality. The universe preserves its sense of mystery, vastness, and the unknown. And there is beauty in this. Beauty in knowing that not everything is attainable, that limits exist, that the universe is bigger than us, and always will be. It is a reminder of humility, that we are a small part of a much vaster cosmos. Seventh, the speed limit gives meaning to distance. In a universe without a speed limit, distance would be just an inconvenience, something to overcome with enough technology. But with the limit, distance becomes something more fundamental. It becomes time. It becomes causal isolation. It becomes a real and insurmountable feature of the universe. This gives meaning to our location in the cosmos. The fact that we are here on this planet, orbiting this star, in this corner of the galaxy matters. It is not just an arbitrary direction we could easily change. It is our home, in a profound sense, the place where we are embedded in the causal structure of space-time. Eighth, the limit allows for the existence of event horizons. Black holes, those regions of space-time, where gravity is so strong that nothing can escape, can only exist because there is a speed limit. The event horizon of a black hole is the surface where the escape velocity equals the speed of light. Inside that surface, not even light can escape, hence the name black hole. Without a speed limit, there would be no event horizons. You could always, in principle, escape from any gravitational field simply by moving fast enough. Black holes could not exist in the form we know, and black holes are fundamental to the universe. They shape the structure of galaxies and control the formation of stars in galactic nuclei. They may have played a role in the formation of the first structures in the early universe. Without them, the cosmos would be fundamentally different. Ninth, the speed limit ensures that the universe has an attainable finite age. We can look back in time by observing distant objects, seeing their light that has traveled for billions of years to reach us, and eventually, looking far enough, we arrive at the cosmic microwave background radiation, the echo of the Big Bang itself. This radiation defines an observable horizon, a limit to how far we can see, not because there is nothing beyond, but because the light from more distant regions has not yet had time to reach us. The universe has a finite age, approximately 13.8 billion years, and we can only see objects whose light has had time to travel to us during that age. Without a speed limit, this observable horizon would not exist. We could see infinitely far, observe the entire universe at once, but then we would have no way to know the age of the universe. Cosmic history would be inaccessible. Instead, the speed limit allows us to be cosmic archaeologists, unearthing the history of the universe by observing objects at different distances and thus at different times. We can see how galaxies have evolved, how stars change, how the universe itself has transformed over time. It is a window into history that is only possible because of the speed limit. 10th, and finally, the speed limit teaches us something profound about the nature of reality. It teaches us that the universe is not arbitrary, not chaotic, not a random collection of unconnected phenomena. Instead, it is a unified system, governed by elegant and profound mathematical principles. Special relativity, with its speed limit, arises from two simple postulates: that the laws of physics are the same in all inertial reference frames, and that the speed of light is constant for all observers. From these two simple principles flow all the strange and beautiful consequences we have explored: time dilation, length contraction, mass-energy equivalence, the unification of space and time. It is a perfect example of how simplicity can give rise to complexity, how a few fundamental principles can generate a rich and varied universe. It is a reminder that the cosmos has an underlying logical structure, that it is not chaos, but order, not confusion, but clarity. And in that clarity, there is beauty. The beauty of the mathematics that describe reality with perfect precision, the beauty of the principles that hold true from the smallest subatomic scales to the largest cosmological extensions, the beauty of a universe that can be comprehended, at least partially, by finite creatures like us. The speed of light limit is part of this beauty. It is not an obstacle but a feature, not a limitation but a definition. It defines what kind of universe we inhabit, one with causal structure, with connections between space and time, with horizons and mysteries, with rules and limits. And within those limits, all the richness of the cosmos flourishes. Stars shine because mass can be converted into energy. Planets orbit because space-time is curved. Life evolves because causality allows the past to influence the future. The mind emerges because information can be processed reliably. The universe can know itself through us because there is order in the apparent chaos. So, perhaps the question is not, why can't we travel faster than light? But rather, why would we want a universe without this limit? A universe without the speed of light limit would be a fundamentally different cosmos, possibly one where complexity, life, and consciousness could not exist. We live in a universe that has limits, and those limits are not prisons, but foundations. They are the rules of the game, the constraints within which creativity can flourish, the edges that give shape and meaning to everything that exists. And when we look at the stars, knowing we can never reach them easily, that they are separated from us by vast abysses of space and time, perhaps we should feel not frustration, but awe. Awe that such a vast cosmos exists, awe that we can comprehend it, at least partially, awe that we are part of it, subject to its laws, molded by its limits, inhabitants of this particular universe, among all possible universes. The speed of light is not just a number, 300,000 kilometers per second. It is a statement about the nature of reality. It is the thread that connects space with time, cause with effect, energy with mass. It is the limit that defines the possible from the impossible, the attainable from the eternally distant. And at the end of this contemplative journey, perhaps the deepest lesson is this: that limits are not the enemies of wonder, but its architects, that the impossible gives meaning to the possible, that the frontiers of knowledge are not walls confining us, but horizons inviting us to explore more deeply, not outward toward the unreachable stars, but inward toward the understanding of the laws that govern all that is. Thank you for joining me on this impossible journey. Thank you for contemplating with me the mysteries of the cosmos, the limits of physics, and the nature of time and space. And if these nocturnal reflections have helped you see the universe with new eyes, consider joining us on Night Science for more explorations of the deepest enigmas of existence. The universe has limits, yes, but within those limits, there is infinite wonder waiting to be discovered, and that, perhaps, is the greatest beauty of all. Good night, and may your dreams take you to places where time and space intertwine, where light traces paths through the darkness, and where every limit is an invitation to comprehend more profoundly the cosmos we call home.